have an idea of what variable we have to apply the induction on. Okay, that comes from experience. So go through these things honestly, clearly, and go through these things many times if you want. Eventually a point will come where you will know yourself what is the variable where you have to apply induction. Because here we are applying induction on cardinality of A. So same when you start with the smallest value. When cardinality of A is equal to 0, we have A equal to empty set. In that case, cardinality of P of A is equal to cardinality of power set of the empty set is equal to cardinal. Okay, what is power set of empty set? We have already calculated this. Since the empty set has only one subset, namely itself, this is the set. Don't make the mistake of writing empty set here without any brackets. Okay, that would be a terrible mistake, because power set of empty set has subsets of empty set, and there is only one subset, the empty set itself. Okay, so this is not 0, but this is 1, because this is a singleton set. And that is equal to 1 can be written as 2 to the power 0. In fact, we have already seen this. And this is nothing but this. So, at least when cardinality of A is 0, this formula is true. So that is our basis for induction. Now we assume the induction hypothesis. Assume that this is equal to this for any set with A with cardinality of A equal to K, where K is some natural number. Where K is some natural number. Okay, let B be a set with cardinality of B equal to K plus 1. We have to prove this. This is what we have to prove. Okay. Now, okay, what can we do now to prove that? This is my basis for induction. This is my induction hypothesis. Now I want to perform the induction step. So to do that, we look at the subsets of B, because we want to estimate the size of power set of B. That means the set of all subsets of B. The subsets of B, or I should have written like this: each subset no, not this. Before this, something else comes. Since, just like the previous one, C, here we have B having K plus 1 elements. Since B has K plus 1 elements which can never be 0, B is not equal to empty set. So there exists there exists an element B belonging to B. Okay. Now we are concerned about subsets of B. So each subset of B either, I think I am running out of ink. Give me a moment, okay? Let me refill. Okay. So let us resume. Now, each subset of B either contains small b or does not contain small b, because that is natural, right? So it's like this. This is B, this is small b. Any subset of capital B may either contain small b or it may be like this also, that does not contain small b. So, and these are the only two types of subsets of capital B. Now we have to estimate the number of each type. I mean the number of subsets in each type. The number of, or yeah, it's better to think of the number instead of thinking of the set, because the number is what we want. The number of subsets of B not containing B is actually what? Any subset that does not contain this small element B is actually a subset of B minus B, and any subset of B minus B does not contain small b. Okay, so this is cardinality of power set of B minus B. Now what is B minus B? I mean, what is the cardinality of B minus B? Cardinality of B minus B, because B has k plus 1 elements, and from them we have removed small b, we have removed one element, so that means the cardinality is k. And whenever the cardinality is k, we have assumed that the actual formula is true. So that means this is equal to 2 to the power cardinality of B minus B. And this is k, we already know. So 2 to the power k. Okay. Again, the number of subsets of B containing small b is what? That is also 2 to the power k. But why? I mean how? Let us take a small example and see how. Suppose my B is this. One, two, three. Okay. And my small b is 3. So we already know what the power set of B is. The empty set, the singleton. In fact, we calculated this one. If you recall, while introducing power sets, we took this very example. This is the power set of B. Now, how many of the sets here do not contain 3? The empty set, this one, this contains 3, this one, these 3 sets contain 3. So you can see that these sets which do not contain 3, they constitute power set of 1, 2, which is nothing but power set of B minus B. That's why the number of elements, the number of subsets of B not containing 3 is the number of subsets of B minus B. This. Okay. So that is equal to 2 to the power k. But what about the number of subsets of B containing 3 or containing small b? This one, this one, this one, and this one. So what are they actually? Containing 3 means you just introduce 3 to these subsets. Okay. They did not contain 3. You take union of 3. You insert 3 here, you get this. You insert 3 here, you get 1, 3. Insert 3 here, you get 2, 3. Insert 3 here, you get B. So again another 2 to the power k subsets. Okay. That's why those subsets of B containing B in number is 2 to the power k, and those that do not contain B are also 2 to the power k in number. Hence, the number of subsets of B is the cardinality of the power set of B is equal to the number of those subsets which contain B or which do not contain B is 2 to the power k plus those which do contain B 2 to the power k, which is 2 times 2 to the power k or 2 to the power k plus 1, and k plus 1, if you recall, is nothing but this. So we have proved this where B is a finite set having k plus 1 elements. This completes the induction. Hence, cardinality of PA is equal to 2 to the power cardinality of A for any finite set A. This has been proved. So these three things we have proved, and in doing so, we have used how to, we have seen how to use the principle of induction. Okay. Actually, it's called the principle of finite induction, but to distinguish it from something called principle of transfinite induction, but that is something else entirely. We will see that in due time when we come across well-ordered sets